Picture this. A swarm of drones darts through a dense forest, dodging trees and changing direction mid-flight with surgical precision. They're faster, quieter, and more agile than anything the military's ever used. Here is the kicker. They run on a newly designed motor tilting mechanism, and it's invented by a 17-year-old. Meet Cooper Taylor, high school student, engineering prodigy. And the mind behind a drone design so groundbreaking, the US Department of Defense bought it. This is the story of how one teenager's innovation might just change the future of flight. Chapter 1. Conventional drones. Drones have come a long way from novelty toys buzzing around backyards to sophisticated tools for aerial photography, surveillance, and even frontline warfare. What once seemed like a distant future is now the standard equipment in military arsenals across the globe. But despite all the advancements in design, software, and flight capability, conventional drones still suffer from critical limitations that can't be ignored, especially in high-stakes environments where every second counts. Let's start with agility. Most traditional drones rely on fixed rotor designs, those familiar four-propeller setups you see on consumer quadcopters and military surveillance units alike. These setups are fine for steady flight in open air, but once you enter a confined space, like an alleyway, dense forest, urban combat zone, or inside buildings, their maneuverability quickly falls apart. Sharp turns become sluggish. Sudden directional changes are slow and imprecise. Why? Because their rotors aren't built to pivot. Vertical and horizontal movements often require a full reorientation of the drone's body or complex pre-programmed commands. There's no graceful transition between forward motion and an upward climb, just jerky, energy-wasting shifts that reveal the drone's location and burn through battery life. That might be acceptable for hobbyists, but for military operators, it's a serious liability. A drone that hesitates in a hallway can cost lives. A craft that buzzes loudly during a stealth operation gives away your position. These design flaws create delays in response times, increase acoustic signatures, and reduce the stealth factor. 3 things you definitely don't want when lives and missions are on the line. So the challenge became clear. Could you build a drone that flies with the agility of a hummingbird, darting, weaving, hovering in place while still carrying the sensors, processors, and payloads of a military-grade machine? It seemed impossible. Then came Cooper Taylor. An aerospace prodigy with a background in biomechanics, Cooper didn't just look at drones, he studied birds, insects, and even fish to understand how nature achieves effortless movement in complex environments. His breakthrough? A completely reimagined propulsion system. One that doesn't just rotate, it tilts. And that changed everything. Chapter 2. Who is Cooper Taylor? Cooper wasn't working in a government-funded lab at MIT. He wasn't shadowing engineers at Lockheed Martin or sitting in on classified briefings at a defense contractor's HQ. He wasn't even old enough to vote. He was just a teenager with a head full of ideas, scribbling sketches in the margins of his notebooks and on the back of cereal boxes. His lab? A bedroom cluttered with wires, batteries, and half-disassembled drones. His workshop? The garage where tools were borrowed from his dad and drone parts were salvaged from crashed RC planes and discarded toy copters. He didn't have corporate funding. He had allowance money and birthday gift cards. But what he lacked in resources, he made up for in raw curiosity and determination. He had one burning question that kept him up at night. What if drones could tilt their motors instead of just spinning them? It sounds simple, but no one had done it quite like Cooper imagined. Most drones relied on fixed motors, rigid frames, and software to do the hard work of maneuvering. But Cooper thought differently. He wondered, what if movement wasn't just about speed or thrust, but about direction, flexibility, and control? By changing the orientation of the motors themselves, maybe a drone could move more like a living creature, adaptable, nimble, and intuitive. At just 17 years old, with zero formal engineering education, Cooper combined his self-taught 3D modeling skills, online tutorials, and a box of broken parts to bring that idea to life. His first prototype was rough. It wobbled, it crashed, it caught fire once, but it worked at least enough to prove the concept. The motors could tilt, and with them, the entire flight dynamic changed. That one shift of tilting the motors changed everything. Suddenly, the drone could strafe sideways without turning its body. It could hover, bank, pivot, and dive with unprecedented control. It didn't need to reposition or fight against its own inertia. It could react instantly. Cooper hadn't just built a drone, he'd redefined what drones could be. Chapter 3. The Motor Tilting Mechanism. Explained. In traditional quadcopters, the design is relatively simple. 4 motors, 4 propellers, all fixed in place. To control movement, these drones rely entirely on changing the speed of individual rotors. Want to go forward? The rear motors spin faster? Need to turn left? The right side motors slow down. It's a clever use of physics, but it has its drawbacks. Mainly, it's not very efficient when it comes to rapid maneuvering or complex flight paths. The drone always has to fight against its own design limitations to change direction. Cooper Taylor's breakthrough flipped that idea literally. Instead of keeping the motors fixed, he mounted each one on a pivoting arm. These arms could tilt in multiple directions forward, backward, and side to side without altering the drone's entire frame. With this innovation, the drone wasn't just adjusting how fast the rotor spun, it was adjusting where the thrust went. That single change introduced something drones had never truly mastered before: vector thrust control. With vector thrust, the drone could do what once required complex acrobatics. It could change direction instantly without banking or tilting its entire body. It could ascend or descend rapidly without needing a drastic pitch adjustment. It could accelerate or stop on a dime, thanks to the ability to redirect thrust in milliseconds. The difference isn't just performance, it's control. The pilot, or onboard AI, can make fine adjustments in real time, making the drone feel less like a machine and more like a natural extension of the operator's intention. Imagine trying to turn a vehicle by varying the speed of each tire. Tedious, right? Now imagine being able to rotate each wheel sideways instead. That's the leap Cooper's design made. By tilting the motors themselves, the drone no longer has to fight physics, it works with it. This was more than just a cool trick. It opened up a world of possibilities. Tighter spaces, faster reaction times, and the kind of fluid motion that's essential in high-risk environments. Chapter 4. 2 key takeaways. 1. Agility like never before. This design isn't just a cool trick, it rewrites the rulebook. The introduction of motor tilting mechanics fundamentally changes what a drone can do, especially in environments where speed, control, and precision are everything. It's not just about flying anymore, it's about how you fly and what you can do mid-air that was previously considered impossible for conventional drones. However, with tilting motors, drones gain a level of agility that was once reserved for fiction novels or movies. Instead of rigid, pre-planned movements, these drones can respond dynamically to their surroundings. They can hover with pinpoint accuracy, even in turbulent crosswinds that would normally push a standard quadcopter off course. The ability to direct thrust in real time gives the drone the capacity to make micro adjustments constantly, keeping it stable, level, and under perfect control. They can also fly through tight, narrow spaces at significantly higher speeds. Traditional drones have to slow down to navigate doorways, hallways, or cluttered areas because their frame orientation is fixed. But Cooper's tilting system allows the drone to glide sideways, pivot around corners, and glides through obstacles, all without ever needing to change its overall position or even lose momentum. Additionally, collision avoidance becomes smarter. Because the drone can redirect itself instantly, it can respond to sudden threats such as walls, falling debris, and enemy fire with a quick flick of its motor angle. It doesn't need to calculate a full reposition. It just shifts its thrust and moves out of the way. Now you see why the military, particularly the Department of Defense, took notice. Today, in reconnaissance and urban combat situations, this kind of agility isn't just a nice feature. It can be the difference between mission success and catastrophic failure. The ability to send a drone into a tight alleyway, up a stairwell, or through a shattered building without losing stability or speed is a game changer. It means faster intel, safer missions, and more confident decision-making on the ground. For a teenager to solve this, that's not just impressive, it's revolutionary. Cooper Taylor didn't just tweak a drone, he redefined what drones are capable of. 2. Less noise, more stealth. By directing thrust rather than relying solely on rotor speed, motor tilting drones gain a serious edge in both efficiency and stealth. Traditional quadcopters make noise, lots of it. Their flight depends on rapid, continuous changes in rotor speed, creating a high-pitched whine that can easily give away their position. But with Cooper's design, movement comes not just from spinning faster, but from changing the direction of the thrust itself. That subtle shift reduces the need for constant acceleration and deceleration, which in turn means the motors don't have to work as hard or as loudly. The result? A quieter, cooler, and more efficient drone. That translates directly to 3 massive tactical advantages: quieter operation, making it harder to detect acoustically; lower heat signature, which is critical for avoiding infrared sensors; longer flight time, thanks to more efficient energy use. In tactical scenarios, especially those involving reconnaissance, covert observation, or behind enemy lines, silence is more than golden, it's survival. Every decibel counts. A traditional drone announces its presence before it even comes into view. Cooper's motor tilting drone, on the other hand, can glide past unnoticed, sounding more like a distant hum than a flying blender. This isn't just about stealth, It's about staying in the air longer, using less power, and reducing the risk of detection on multiple fronts. Cooper's design brings drones closer to the fluid silence of birds and farther from the clunky buzz of machines. It doesn't just fly, it disappears. Chapter 5. The Pentagon Comes Calling. Word spread fast, faster than Cooper ever expected. What began as a garage-built prototype and a curious teenager asking, "What if?" quickly became one of the most talked about innovations in drone design. Within just a few months of uploading his designs and demo videos to online forums, YouTube clips, CAD schematics, people took notice. Not just hobbyists or fellow tinkerers. It was engineers, researchers, executives at drone startups, and even defense analysts. And then, the US Department of Defense reached out. At first, Cooper thought it was a prank, a formal email, then a phone call, then a video meeting with officials who weren't just impressed, they were intrigued deeply. These weren't just casual inquiries. The questions were clear and specific. Indeed, they knew what they were looking at. Cooper's tilting motor drone was more than an innovative concept. It had real-world, battlefield potential. Within weeks, they made an offer to purchase the patent, bring the design in-house, and explore its applications across multiple branches of the military. And it wasn't just about surveillance. The Pentagon saw opportunities across the board: reconnaissance missions in tight urban zones or dense jungle terrain, autonomous resupply drones capable of landing in small, hostile spaces, battlefield logistics moving gear, sensors, and supplies with speed and agility, search and rescue operations in collapsed buildings or natural disaster zones. The Pentagon doesn't place bets lightly, but they bet on a teenager, a kid who sketched in a notebook and soldered pieces in his garage. And they weren't just buying a blueprint, they were investing in an idea, a new direction for drone mobility, one that could shape how future missions are carried out. Cooper's design had moved from digital forums to defense briefings, from the garage to the government, from concept to classified, all because he asked the right question and refused to settle for the limits of what already existed. Chapter 6. Challenges and Future Possibilities. The mechanism isn't perfect, at least not yet. Like any groundbreaking technology, Cooper's motor tilting system comes with its own set of engineering challenges. Unlike conventional drones that rely on fixed motors and fewer mechanical components, this design introduces more complexity. More moving parts means more opportunities for wear and tear. Each tilt mechanism adds another potential point of failure, whether that's a misalignment or a software hiccup during a rapid maneuver. And then there's the weight. The tilt actuators, while compact, still add to the drone's overall mass, and the added hardware can eat into payload capacity. It's a delicate trade-off between control and efficiency, one that engineers are constantly refining. But here's the exciting part. Those limitations are shrinking by the day. Advancements in lightweight composite materials, micro actuators, and AI-assisted flight stabilization is rapidly closing the gap. Modern drones are becoming smarter, lighter, and more adaptive. Fitted with onboard processors running real-time flight corrections, the margin for mechanical error narrows significantly. It's no longer a question of if the system can scale, it's a question of when. And the possibilities? That's where things get interesting. Imagine drones capable of precise navigation through collapsed buildings during search and rescue operations, slipping through cracks, hovering beside survivors, delivering supplies. Think about next-generation space drones, designed for zero-gravity maneuvering on orbital missions or asteroid exploration, where the ability to reorient thrust instantly could be a game-changer. Or civilian drones that can land on moving vehicles with pinpoint accuracy, delivering packages to ships at sea, ambulances in transit, or remote teams on the move. Cooper's breakthrough isn't just a solution to today's drone limitations, it's a foundation for tomorrow's aerial robotics. He didn't just imagine a better drone, he cracked open an entire new category of possibilities. Chapter 7. A New Generation of Innovators. This story is much bigger than just drones. It's about far more powerful than machinery or patents. It's about what happens when young minds challenge old systems, when curiosity outpaces credentials, when innovation isn't confined to labs or limited by experience. Cooper Taylor didn't have a degree, a grant, or access to state-of-the-art equipment. He had questions, he had persistence, he had a garage, a laptop, and the willingness to fail again, and again, and again, until something clicked. And that willingness to keep pushing, to keep tinkering, to keep wondering what if, is what truly defines innovation. His design isn't just a feat of engineering, it's a reminder that brilliance can come from anywhere, that the next big breakthrough might not emerge from a billion-dollar research facility, but from a basement, a classroom, or a quiet corner of someone's imagination. Because if one teenager with no formal training and no corporate backing can redefine the future of flight, What could the next one do? What could happen if more young people were given the space to experiment, the tools to explore, and the confidence to challenge the way things have always been done? Cooper's story is a spark, not just for the drone industry, but for an entire generation watching from the sidelines thinking, maybe I could do something like that too. And they can, because this isn't just about tilt rotors or thrust vectors. It's a story about human potential, about what's possible when curiosity is allowed to lead. It's about building more than machines. It's about building belief. The future doesn't belong to those with the longest resumes. It belongs to the bold, the curious, the restless, and the next generation of innovators. Motor tilting drones could soon be the new standard, not just in warfare, but in rescue, science, and daily life. And it's hard to believe, it all started with a question from a young man who wasn't afraid to try something different. What would you build if the world wasn't watching yet? Also, tell us in the comments, what problem would you solve with your own invention? If this story inspired you, hit subscribe to watch more stories at the intersection of innovation, technology, and science. Like this video so more people can hear the story, or add a suggestion for the next video. Thank you for watching. Stay blessed, stay curious, and never stop building.